CERN, the people who last brought you the internet, present the Large Hadron Collider in particle physics and you. You, sir. Yes, you. Know much about particle physics? Ever wondered what the fabric of the universe is? Don't you care to know how the universe you live in works? Well, you should be. Ever heard of dark energy? Ever heard of multiple dimensions? Scared? Well, don't be. Once you understand these concepts, you'll realize how complex and exciting the world we live in is. Ready to learn? Good! To fully understand the different theories and ideas of nuclear physics, we must first go to the beginning of our universe. According to the most accepted theory of today, about 13.7 billion years ago, the entire universe was compacted, extremely dense, kinda like that egg. Imagine all of the universe packed beneath the shell, infinitely compact and extremely hot. Then suddenly... boom! The universe burst from its condensed state and began expanding in every direction. And for just a few moments, the universe was hot, about 100,000 degrees hotter than the center of the sun. But as it expanded, it cooled down, and quarks and electrons, two fundamental particles of our universe, were produced, and then the quarks began to combine to make protons and neutrons, and soon, about 380,000 years later, electrons finally began orbiting around nuclei, and the first atoms were born. Tastes good, doesn't it? Well, that's only about 4% of the universe. That's right, only 4% of the entire universe is made out of atoms. That means everything you see around you, even when you gaze out into the cosmos, composes about 4% of the actual universe. The other 96% of the universe is invisible to our eyes and consists of dark matter and dark energy. Out of the remaining 96%, dark matter accounts for about 26% of our universe. Dark matter is a hypothetical form of matter, meaning no one has ever seen it, but it has been observed through the effects gravity has on it. Let me explain. Look at this spinning galaxy. Everything looks normal, right? Wrong! That galaxy, like all galaxies, is spinning too fast for the amount of mass that is visible. You see, the stars near the center of the galaxy are spinning with a faster velocity than they should. The ratio of mass to velocity doesn't add up. For this reason, physicists have determined that there must be more mass that exists that they just can't see, and that is dark matter. Dark energy then makes up the remaining 70% of the known universe. Unlike dark matter, dark energy is theorized to be homogeneously spread throughout the entire universe. Just as elusive as dark matter, dark energy can be observed indirectly through the mind-boggling effect it has on our universe. We know that gravity works against all matter, so right after the Big Bang, when particles were soaring through space, gravity should have been pushing them back, and thus slowing down the expansion of the universe to an inevitable halt. But the universe is still expanding at an exponential rate. This would require an enormous amount of energy. Physicists have dubbed this mysterious force as dark energy. Unfortunately, the mysteries don't end there. Let's go back to the 4% we do know about. We know that everything around you, including yourself, is composed of matter. We also know that all matter has a mass. But what is mass? We measure in grams and pounds and ounces, but what exactly are we measuring? It's simple, really. Take Einstein's famous formula, E equals mc squared. Let's simplify it a little. There we go. Mass is actually just stored energy, but when we get down to the smallest, most fundamental particles like electrons, there's a problem. Since an electron is an elementary particle, as in it's not composed of any smaller particles, then it shouldn't have a mass, right? Ah, but it does! How does something that's made up of nothing have a mass, then? Not so fast, Einstein. I'll take it from here. Well, physicists believe that when the Big Bang happened, a field was created, one that spread throughout the entire universe. Now, when particles such as electrons interact with this field, let's call it the Higgs Field, they gain mass grouping with another elementary particle, the Higgs boson. So when these particles interact and group, they create mass. It's quite a complicated procedure, so let's break it down. Say you're an electron, small and massless, flying at the speed of light. And let's say this creepy man that's been watching you this whole time is a Higgs boson. He's been waiting for you this whole time and has now decided to interact with you. While you are both massless fundamental particles, this interaction has caused you to slow down and gain mass. Now while this all makes sense, there is one big problem. no one has ever seen the Higgs boson. He is as mysterious as he is creepy. His presence is just implied by your newly gained mass. So if this the Higgs boson, actually exists, then that would explain the mystery behind why all matter has mass. Because when you come down to it, you and all the matter you see are composed of these fundamental particles, all massless, yet you and everything else seems to have a mass. Well, now that we've discussed all these mysteries and theories, want to find out some facts? Oh, so now you care about understanding the fabric and structure of our universe. Well, okay, I guess you've deserved it. But there is just one little problem. Everything I just explained to you, while being implied through many studies, is still all just theory. That's right. Better get to work testing all these theories and discovering the truth. Frustrated? Well, all the math in the world won't solve the mysteries. You need good old-fashioned hard evidence. And the only way to get that is through experimentation. But where to start? The beginning is a great place to start. Let's take another look at our Big Bang. In the moments right after the Big Bang, all the building blocks of the universe should be present. We should find some answers there. But wait! The Big Bang has already happened. We kind of missed our chance 13.7 billion years ago. Oh well, it was a good idea at the very least. But what if we could recreate the Big Bang? That would probably take a machine costing billions of dollars and about 15 years to build, and probably the collaboration of about 10,000 scientists and engineers. Good thing CERN, the European Organization for Nuclear Research, has done just that! That's right! For the past 15 years, CERN, along with 10,000 scientists and engineers from around the world, have been creating the world's largest particle accelerator, dubbed the Large Hadron Collider. Located 100 meters underground and spanning a 27-kilometer radius across the France-Switzerland border, the LHC is a triumph of ingenuity and collaboration. But wondering how a giant particle accelerator is going to recreate the Big Bang? Well then, let me show you. Let's say you're a proton, and so is your mustachioed friend. What they've done is create a large circular ring like this track in which they can accelerate protons around. So you, the proton, as well as your groomed friend, another proton, will be shot around the ring in opposite directions. With the use of magnets, each lap the proton takes, it will gain more and more speed. Until finally, they reach 99.999% the speed of light. Then, with an adjustment of the magnets, they collide. And voila! When the protons collide, the quarks and gluons they're composed of break apart, and the same amount of energy that was present 3/millionths of a second after the real Big Bang is released, giving us a glimpse into the events that unfolded 13.7 million years ago. While this is happening, two giant machines, Atlas and CMS, will be recording all the data at incredible speeds in order for physicists to view and interpret. Working like a camera, Atlas and CMS will take around 40,000 pictures a second to try and record data from the collisions. And if the idea of just one light-speed collision of protons seems amazing to you, how about a collision every 25 nanoseconds? The understanding we can get from these experiments is potentially groundbreaking. Once the pictures have been taken, scientists can study them to see if dark matter was created in the collision, if dark energy was released, and if the Higgs boson made a guest appearance. Just like Columbus sailing to the New World, physicists cannot wait to see what shore of information and discovery they land on. The more we know about the composition of our universe, the more we understand the history and future of our world. While there are animals that can use tools, communicate in languages, and even build advanced structures, only humans have the capability to study themselves and the world around them just for the sake of knowledge alone. It is this kind of curiosity that has rocketed the human race forward in understanding and development across all fields of study and science. So, know your physics, understand your world, and support your local LHC!